So chemistry and measurements. There's a lot of reasons to take a look at this stuff. Here's some practical ones. Like 63% of all wrongful convictions were due to errors in the lab, right? I like this one about the Patriot missile failure, right? The NASA was collaborating with a European company. The European company sends some information in the metric system, right? Well, our guys plugged things in miles per hour, so there was this, they forgot to convert, or they made the incorrect conversion, and boom, right? Oh no, that was a Patriot missile. That was something that's due to rounding. There was, oh, I don't have a picture of it. There's this little Mars rover they sent that crashed due to miles per hour and meters per second. This is something else. This is due to rounding, and we're going to talk about rounding too, how to round measurements. Okay. So matter. So let's go ahead and get started here. Gabriella, what is the difference between an element and a compound? Oh, I was going to hand out my template and I forgot. Yeah, and where are they all? Where are they all? All the elements? Yeah. In fact, this thing is off by like 3 now. We're up to 117. I think the last one that they just verified, Russia did, Unan Pentium or something. I don't know what the heck, right? These things, but anyway, they last for a very brief amount of time, but it exists. But here's all the elements, right? And then I kind of interrupt her. What's the compound then? Yeah, combine them, right? Combine them, you'd have a compound. It gets kind of confusing because you could take, oh yeah, that's true. Yeah, it takes pretty much anything, and put them together, you'd have the compound. There's several different types of compounds, but we're not worried about that right now. So here's our table of matter, right, and how it's divvied up. All matter, right? It's either a substance or it's a mixture, and you can go in between mixtures and substances, right, by just doing physical processes. Physical, so you're not changing anything, right? It's kind of taking a mixture and divvying it up into its pure components, okay? We have some fancy machines upstairs that do that. If you have like a Coca-Cola, I have a can of it, there is no mystery anymore because we can go upstairs, put a sample of this on the machine upstairs called a high-performance liquid chromatograph, and not only will we know what all the little ingredients are, but we'll know exactly how much of each ingredient's in there. So there really aren't any secrets anymore. We just can't reproduce it and go sell the stuff. Okay. The substances, you can break them up into what Gabby was saying, elements or compounds. Now there we can jump between one or the other. That's chemical reactions. If you have a mixture, a whole bunch of different things mixed together, right? There's one of 2 types of mixtures, homogeneous or heterogeneous. What's the difference between these 2? How could you recognize the difference? Do you know, Maria? How could you recognize the difference? Same, really, really close. Now, there are different components in there, so they're both mixtures, but it just goes by the eyeball. Homogeneous just looks the same throughout. They call that homogeneous. If it doesn't look the same throughout, oil on top of water, it's a mixture, but that doesn't look the same throughout, heterogeneous. They just go by the eyeball. Okay. Now the eyeball includes the microscope thing. If you have big globules, hunks of dirt floating in there, they call that heterogeneous. But I don't know. Okay. How about, where does this stuff fit in here? In our table, Daniela, if you were going to, hey, I have water, where would it go in this table? Ooh, it's supposed to be a trick question, and she got it. Why isn't it not? I wanted her to say what? I wanted her to say this. right? But where did I likely get the water? From here, right? So is it pure H2O? No, it's not. So there's like you can see this calcium carbonate, and there's some iron, and there's some other little things dissolved, and maybe some little microbes or something, I don't know. Can't be too bad because we drink it. So the best explanation for water that you get from the tap would be homogeneous mixture, right? In fact, it's hard to keep it not from being a mixture because gases from the air just dissolve in there. It's pretty hard to have just pure CO2, pure water, I mean. How about salt and water? Take some salt. Let's see. I don't have any. Here's water. Yeah. Well, you can see this. I'm going to pick on Shannon. Okay. Salt and water. What would you call that? All right, we got to look careful at it. It's not the same throughout, though. It'd be heterogeneous. But if you sit there and go like this, right, then it would be homogeneous, right? Get it all to dissolve. It can even be a little cloudy. That's fine, as long as it looks cloudy all throughout. Okay, it doesn't have to be clear. It just has to look the same throughout. A water and a dye. Let's see here. Pretend all my salt was dissolved. Take a dye. Ebony. There. Homogeneous or heterogeneous? Does it look the same throughout? No, so it would be heterogeneous. But then you sit there and you wait long enough, all right? You just have to wait a while. I don't know how long you'd wait. Maybe, I don't know, 10, 15 minutes or so. It'll be homogeneous. Come on in, Andromeda. Okay. So that's some practice on identifying compounds on the table. But how about these chemical or physical processes? When we're jumping from elements to compounds, or if we're jumping from mixtures and breaking them up into their pure substances. This is where it gets a little complicated. This is probably the most boring demonstration I can get. Let's pick on Andromeda. She just came in, right? Sitting here and watching ice melt, right? Would that, oh, I lost it. Would that be a chemical or a physical process? Right? Right here. Would that be a chemical? Or now, the question I really ask myself is, at the end of this process, do I get a different compound? Do I get something different? If you do, it's a chemical process. But if you get the same thing again, it's physical. So you end up with ice melting, you're starting with solid water, ending up with liquid water. So it's still water. So it would be a physical process. Right? There's a lot of them here. Look at this stuff. Right? What is this? What's the word for this stuff getting all wet out here? Starts with a C. Condensation. All right? Chemical or physical process? Anybody? Physical. Because you have water gas going to water liquid, physical. There's another one that you can't see. This is how snow disappears in Minnesota or up north in Antarctica or something. Solid to a gas. That starts with an S. We're getting ahead of ourselves, but it's okay. Ooh, sublimation. Good memory, right? So yeah, another physical or chemical process. Going from a solid water to gaseous water, physical process. Right? Water's water, doesn't matter what state it's in. Okay, how about steel wool and fire here? So you take some steel wool. I wonder if I can just do it this way. All right. Physical or chemical process? Most definitely chemical, right? You're not ending up with iron anymore. You're ending up with pretty much rust. It's, why can't I do this, though, to a nail, right? Or this thing? It's all surface area, right? You heat up anything that high, it'll oxidize. We're jumping ahead, but it'll react, okay? So it's just surface area. That's why that works. So I never thought about it being dangerous to work in a steel wool factory, but I guess it's not too safe, right? Because this stuff burns. Distillation. Okay. If you're in the oil business, right? The Arabs, they have what in their how does that work? They have what in the desert there? A whole lot of black gold, a whole lot of oil, right? Well, you get everything from that. You get jet fuels, you get our gasoline, you get a lot of different chemicals, right? Well, all these different chemicals have different boiling points. So all they do is they distill the oil, right? So just imagine this is the black stuff. Now it's going to have a lot more than 2 different components in it. It's going to have a lot. But they're all going to have different boiling points. Some are going to boil, they boil off really a lot easier than others. So what they're going to do is just put a big flame under this, and it's going to be a big refinery. It's much more complicated, but this is the idea, right? They're heating it, okay, and they're monitoring the temperature. And then they see that this blue stuff is coming off. See how the blue stuff is boiling up higher? It's really cold around here, and it's condensing. So the blue stuff comes off first. Now the blue stuff is all gone. Now the red stuff is starting to boil. But I don't know if you noticed, I probably didn't have it high enough here. The thermometer really shot up. So right when these computers, right when this guy, right when the temperature starts going up, they change a valve, right? Because now maybe the jet fuels have boiled off. Now we have gasoline coming off. You don't want to mix the two. Otherwise you got to distill it again. So once that temperature starts going up, the computer recognizes it, changes the valves. Now all that condensate, all that liquid goes to a different big, huge container, right? And it'll monitor the temperature. Once it starts changing a little bit, ding, goes to the other one, right? So they get pure components out of that big vat of oil. So it's pretty neat. Okay, significant figures. Last time we met, in lab, we were talking about just practicing on the calculator. And how many digits do I write? How many digits do I write? Well, now we can finally answer the question and put some terminology to it. But I need some help here to get us going. How about Maria? Maria and Daniela, I need your help. Maria? Let's see something that would work here. Let's see here. I just want to find some. Okay, this will work. So what we're going to do, Maria, let's do this. Oh, we can write it up here. Here's our 2 rulers, right? They're in centimeters, okay? And I'll give Maria the crappy one, right? So just try to do your best in centimeters and try to measure across here. Do your best. This is the one without lines. So what would you say it is? About 45. Right? And that's centimeters, I think. Okay. And then Gabriella. Whoops, I gave you the wrong end. There you go. About 45 and a half. Okay. Ooh. Maria did pretty good, huh? Right? With that ruler. But the point I'm trying to illustrate is, now I got to put units on here. Very often, this is all we see. right? Whether it be in the newspaper or in a homework problem or whatever, we rarely get to see the tool used to measure. We know this one isn't near as good as this one, right? But when you're talking to people and email discussions, just talking and communicating, this is what you show. So just by looking at the two, who had the better instrument? But how can you tell, though? More precise is a good word. There's more. Well, we don't know if accuracy would be if we got it right. I assume we did. That would be. We'd use the word accuracy if these were all calibrated. I assume they are, right? More information, more digits. The word I'm trying to get you at is sig figs. There's more digits. There's more significant figures. So it has to be a better measurement. Okay. But everything you said is right. Okay. So if this is a better measurement. If we added the two, if we add a good measurement and a bad measurement, what's the result? Well, there has to be some rules for this, and there is. What if you multiply a bad measurement times a good measurement? What's the result? How many digits to report it to? There's rules for that, right? You multiply the two together and divide by 6. What's the rules? See, there's the rules for all that. So that's what we're getting at. But first, we need to be able to recognize how many significant figures are in a measurement. And there's a hard way and an easy way. We're going to do the hard way first, which really isn't that hard. But how many sig figs would you guess are in, Shannon, 3.80 centimeters? There's 3. Just imagine Maria or someone. Yeah, just imagine Maria or someone staring up here. It was really Gabriella. She was staring up here. What if she would have said 45.0? You would have known, because she spent a lot of time staring to get that 0. That 0 is right. It's significant. So your guess was right. There's 3. There's 3 digits. How about 3.080? Ebony, what would you say for that? Let's guess. It's 4. It's 4. They're all good. They're all good. These zeros are significant. It's 4. C. How about C? What would you say for that, Gabriella? Oh, it's lower. There's only 1. And this is where it gets confused. Otherwise, we always just count the number of digits and we got it right. But there's a trick to this. Yeah, well, I'll show you. You're getting there. How about this one? There's only 2, right? I don't like to memorize stuff, so it looks like you could memorize how to do this, right? If they're in here, you don't count them. They're after you count them. But I'll show you a little better way in a little bit. How about E? Everybody, what would you count there? I count 6. Do you count 6? Yeah, count them all. 6. Okay, so this is the best way, though. You use scientific notation. Write all these numbers in scientific notation, and it's so much easier. Where you have A is a number between 1 and 10, so it'll write it in this format. Let me give you an example. Let's do this one where we said there was just 1. So what we're going to do is move the decimal point until we get our A. It has to be a number between 1 and 10. So I'm going to move that decimal point. 1, 2, I have to move it 3 times, but I stop there. So if I keep moving, I've got 10. So I'd have 1 point, right? Because I moved it over 1, 2, 3 places. So you write times 10 I moved it 3 places. Now this is the part you got to remember. It's negative. Positive exponents is like 10 to the third is 10 times 10 times 10. It's 1,000. 1,000 times 1. That's a big number. So it definitely isn't positive 3. It's negative 3. It's a small number. So negative exponents are small numbers, less than 1. So when you write a number in scientific notation, it's so much easier to figure out the significant figures. Now you just literally count the digits. There's only one. And you can do that for every single one of these. And there's no figuring anything out. You just count. Once you get in scientific notation, just count all the digits in your A figure, and you got it. Right? So go ahead and see if you can fill this out. Right? Well, let's do the first one together, make sure everyone's on track here. Maria, what would be my A digit for this first one? What would you say it is? It's because it's always something times 10 to something. 8.5. Keep going. Right? Because if you move it 1 here, here, stop. Right? Because you're at 8.5. You're between 1 and 10. So now you just write everything that's there. These zeros disappeared on you. So now it's just 8.501. Make sense? Just keep moving the decimal place until you get something between 1 and 10. So these guys are gone. How many times did I move it? I moved it 3, so -3 or +3? Negative. Number of sig figs would be 4. You just count them up. 1, 2, 3, 4. There's 4 digits here, so 4. Okay. So try these. See if you can fill in this table on these, and I'll ask you. Yeah, a lot of times they do that. They don't write in the decimal, but you know it's right here. And then you have to move it 1, 2, 3, 4, 5. You have to move it 6 times. Otherwise, you're not going to have a number between 1 and 10. No, because the decimal point's right here. It's just understood. A lot of times, even you don't write it right. When you write 12, you don't write 12 point, even though you should. Right? Yeah. Yeah, it's $20 though. Oh, you got it? Okay. Great. Thank you. How's it going? Pretty good. If somebody's not sure, just ask. I can help you out.
The limit would be just a positive.
Yeah. Well, and you have to move it over. Keep going until you get it between 1 and 10. So you have to be 3.605, 0001. Right? Because if you stop here, so you're not between 1 and 10. You got to keep going. But 3.65 is. Okay, you may not have got them all done, but we can do a few of these here. Let's do this one. Daniela, what did you get for your measurement in scientific notation for this?
65001 × 10⁶.
Okay. Does everybody agree? Yeah. So she just kept moving the decimal point until she got it between 1 and 10. And how about the number of sig figs in that? Shannon, what would you say for that? 7? 1, 2, 3, 4, 5. I count 6.
There's an addition.
Oh, there's 3 zeros. Oh, I didn't even see that. Thank you. You're right, 7. Okay. Let's try this one. That'll be enough. All right. How about Ebony? How did you write this one in scientific notation? 10 to the negative 4. Okay. So, Gabriella, how many sig figs are there then? 4? You wrote this 0 though, didn't you? There'd be 5. Yeah. So if you write in scientific notation, I think it's so much easier to figure out the number of sig figs, right? So if there's a, so on Friday you're going to be taking a quiz. The homework is like this, right? The quiz is like this. To give you a heads up. Okay, significant figures and calculations. This you just got to know, right? When you're going to add and subtract two numbers, right? We're doing everything on our calculator, but how many digits do you give the answer to? Well, we're going to add or subtract two numbers. Report to the smallest resolution. And resolution is just the decimal place. For example, if I have 5.83 and I'm adding 0.7, I would report my answer to a what place? Now, resolution is just how far do things go? Like this guy, he measured it to the tenths place. This person measured it to the hundredths place, right? So the worst resolution is to the tenths place, so you have to report your answer to the worst resolution. Okay, so you do everything on your calculator, but you report your answer only to the tenths place. Okay, that's what that one means. For example, let's try this one. 1.53 plus 2.0. You don't have to do it on your calculator. It would be 3.53. But how far do you report your digits? What I like to do is I just like to underline this stuff so I don't forget what I'm doing here. Right? I underline the last digit. Because there might be more than 2, and it gets kind of ugly or complicated. So I can say, oh, the 2 measurement, he goes to the tenths place. The other one goes to the hundredths place. So I have to report my answer to the tenths place. So then you do the math, and you get 3.53, but I underline that guy. Okay. But it's probably not the best way to report your answer. You could report your answer this way, but what if someone doesn't know what the heck your underline means? Right? So you should probably just write 3.5. That'd be the best way to do it. Otherwise, hey, what does your underline mean? Right? Now, if that would have been if the 3 over here would have been a 7 or something, would have said 3.6, rounded up. Okay. Let's try this one. Let's try B. So underline the last digit in each question. Sorry, underline last digit in each one there in B. You don't have to underline if you don't want to. Then do it on your calculator. So you figure out which one has the worst resolution. You do it on your calculator. Report your answer to that worst resolution. See what you come up with. Maria, did you get a chance to do it on your calculator? What did you come up with on your calculator? The whole answer in all its glory. Oh, you just wrote down. Okay, what's your final answer? 1.7. Okay. So she's saying the answer is 1.7. She came up with a lot more digits in her calculator. Does everybody agree? I'm not sure what the whole answer is. 1.7, blah, 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 blah. She's right, right? You got to report your answer to that tenths place. That's why I like doing this, because it kind of helps me remind me where the heck I'm doing. Tenths place. That's the worst one. So she's right. Okay, that's when you add and subtract. when you're multiplying or dividing, oh, I think it's easier. Report your answer to the one with the smallest number of significant figures. So like in this mess right here, right? Look at all those, there's 3 measurements in there. So that means they all could have different numbers of significant figures. But figure out which one has the smallest number of sig figs, and then you have to report your answer to that smallest number of sig figs. You report your answer to how many sig figs in this question? 2. So go ahead and do it on the calculator and report your answer to 2 sig figs. Oh, this is a good one. You did it on your calculator. Didn't you get something like 10.26? Right? How do you report this to 2 sig figs? Okay, you could write 10. You could write 10. But then I think it would be better to write it this way, because the dot means that 0 is significant. Sometimes you say 100, 200, or those, you know, we're kind of, that's our language kind of screws us up. But really the safest way is just to write all of our answers in what? Scientific notation. If you write them everything in scientific notation, there's never any qualm, right? So if you take a look at what we just, on the calculator, sometimes you can set this guy up to always give your answer in scientific notation if you want, but this would have to be, move it over 1, so that'd be 1.026 times 10 to the first. Too many digits, though. So I really should write it as 1.0. That's the best way to give this answer. 1.0 times 10 to the 1. That is the best way. Okay. Yeah. It would not be wrong if you did this, though. Or even if, I don't know, that should be okay, too. But the best way, because this may get missed. You may not see the dot or the, but this, you won't get any points taken off for sure. Okay, let's try one that's a little more complicated. Combine the two. C. Okay. So we need to combine the 2 rules. But what I suggest is, if you're going to do this on your calculator, right? Forget sig figs. If you're going to do this on your calculator, what would you do first? What part would you do? Wouldn't you do the parentheses part first, right? Get what that little number is, and then you do the rest. And that's what you have to do too. You have to get the answer here using the rules. Okay? So 3.8 plus 2.72. Let's see. What is 3.8 plus 2.72? Oh, thank you. Oh, 6.52, she says. Okay, so this is 6.52. Now, where am I supposed to be reporting my answer here, according to our rules for adding and subtracting? To the which digit? To the tenths. So I need to underline it. This is where the underlining really becomes important, because you don't do any rounding until all the calculations are done. So you carry all your digits, but you have to recognize, oh, I only have 2 sig figs here. But the number is really 6.52. If there's more, fine, you write them. But I only have 2 sig figs. Now you do the rest. 7.42 times 6.52 times 4.085. But you're going to report your answer to how many sig figs? Just 2. Because you have to look at them all and say, oh, well, he has 3 digits. He has 1, 2, 3, 4. Ah, this one only has 2. So you have to report your answer to 2 sig figs. And when you do it in your calculator, you have to type in 6.52, though. You don't do any rounding to the very end. That's the rules on rounding. So 6.52 times 7.42 divide it by 4.085, and report your answer to 2 sig figs. Daniela, did you get an answer? 1.1 times 10 to the first. Anybody else get that? 1 to the first. Oh, but that's an 8. Right? The digit after that 1.1 is an 8. Right? If I wrote it all out on my calculator, this is what my calculator came out with. 11.8 429, right, blah, 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 blah. So I see 2 ways to give the answer. You could just write 12, right? Or 1.2 times 10 to the 1. Yeah, because this digit right here, right? So you can't write the 11. You're going to have to round up because of that 8. So it'll be 1.2 times 10 to the 1. Or you could write 12. Erase. Okay. Let's 40. Let's try. We'll come back and do some more of these. Let's just wrap these up. Okay. We'll come back and practice some more of those. Base units. We need to know these. You probably know a lot of them already. Length is a meter. This is all the whose system. Metric, right? Science just deals with metric system. It's kind of nice, but length is meter, symbol little m, mass kilogram, kg, time second s, temperature Kelvin with a big K, and a mole. Well, we'll get to that later. Okay. DM, our little prefixes, right? SI prefixes. What is, now this part could be anything. This part could be any of these guys, right? So it could be DM, it could be DS, I guess not the K, right? I'm going to confuse things. It could be, you know, have a G. I don't know why. This is the one part of the metric system that is confusing to me. Why have mass be kilogram? Why not just have it be gram, right? It'd make a lot more sense. But that's their standard unit. Fine. You just got to live with it. But when you talk about the measurements, this little second one, it could be, you know, distance, length, right? Meters. It could be grams. It could be seconds. It could be Kelvin, moles, whatever. So that's the second one here. Here's our prefix, D, C, M, and K. So if you have DM, that's called decimeter. Right? Now, how would you put the numbers in here? If I had 1 meter, how many decimeters would I have? It's all you, I give you a hint. Metric system is all factors of 10. So your answers are always going to be 10, 100, 1,000, something like that. Deci. Deci isn't very, it's 10. Deci isn't a very common word. This one is, though. CM is centimeter. Now this one, I think this is the only prefix that we actually even use in English here, at least in the United States. If I have 1 meter, then I have 100 centimeters. Yeah. Okay. M&M, millimeter. If I have a meter, I have 1,000. So these millimeters are extremely small, right? They're the little tiny the smallest division on here, right? The bigger, let's see, yeah, okay. Km is kilometer. And if I have one, this is where you got to kind of screw things around. If I have 1 kilometer, I have how many meters? Kilometer's a big unit. 1,000. Okay. So when you're doing this, to me, one thing that helps me remember this is when you're trying to make these, oh, how many are of this is in a meter or whatever, the numbers always goes with the prefix, except for kilo, right? Kilo, the number goes with the meter. So 1,000 millimeters, 100 centimeters, 10 decimeters, all that equals 1 meter. So the number almost always goes with the prefix, except for with kilo. That goes with the meters. Okay. And this last part here, remember this, that could be, right? That could be gram, it could be seconds, it could be moles, meters. Okay. And then if you can take some of these measurements and combine them, we've seen this, you've kind of heard of this before. You take like a square, length times width, and you get area, right? Well, if this is 2 meters and this is 3 meters, you just end up with 6 meters squared. So that means this is the unit for area, right? Length times width times height would be meters times meters times meters, meters cubed for volume. And then we have density, just mass over volume. I think we'll talk more about density in a bit, but mass over volume. So you have the mass unit over the volume unit. Sounds weird, kilograms per cubic meter, but that's the standard way in the metric system to write density. And then for volume, instead of using cubic meters a lot, right, they like this liters and milliliters stuff, right, especially in all these drinks. So 1 cubic centimeter is 1 milliliter, right? 1 cubic decimeter is 1 big L, where L represents, what is L called? A liter. Okay. So we have a little density thing here. For density is mass over volume, right? And oh, here's the Coke. Okay, so you take a can of Coke, you put it in water, right? It sinks. Fine. But if you take a can of Diet Coke, let's see, here it is. Take a can of Diet Coke, and put it in water. Does it sink? Why? Has to do with density. Why is this more dense than that? Ooh, yeah, sugar. Exactly. Okay, where is it? I had it here. All right. You drink 1 can of Coca-Cola, that's how much sugar you got, right? Drink 1 can of Diet Coke, that's how much, not sugar, because then it would, it's, anyone know what it's called? Aspartame or NutraSweet, that kind of stuff, right? It's about 10,000 times sweeter than sugar. Now, this is actually a lie. What I should do is make this a better demonstration. Only in Mexico, Mexican Coca-Cola, do they use real sugar. And I've been told that, and I would love to get some, it tastes so much better than the Coca-Cola you can get up here, because they use real sugar. I'd love to try it. We don't use real sugar. What do we use? High fructose content corn syrup. It's this slimy stuff, And it'd be much better. I should get a bag of it and just put it in here, right? Same idea. It's going to be really massive, and it's got a lot of sugar in it, but it's just a cheaper way for us to get the sugar. It's kind of disgusting. Okay, let's go back to those, I think the most difficult stuff for today. See if we can practice some more of those. All right, these. Okay. So let's try, what's the ugliest one there? How about H, right? H looks the ugliest. Let's try H. And then we'll call it a day. Report your answer to the right number of sig figs. Yeah, and that last digit is the significant one. That's what I came up with too. Right. There's way too many digits there.
Wouldn't it be 5 because the first two of the numbers?
Okay, so if you're going to do this in your calculator, you'd do what's in parentheses first, right? So the result you get is right here. But there's only how many sig figs? There's only 2, because you have to report him to the hundredths place, him to the hundredths place. So you got to report your answer to the hundredths place. So there's only 2 sig figs here. Because if you write this in scientific notation, it'd be 1.6 times 10 to the negative 1. So only 2 sig figs here. Here there's 1, 2, 3, 4, 5. So you report your answer always to the worst measurement. So you can't report it to 5 sig figs. You got to report it to 2. So this has way too many sig figs. I can only report it to 2 sig figs. So I have to report it as what? 2.3 times 10 to the third. 1, 2, yeah. 2.3 times 10 to the third is how you'd have to report your answer. That's the best way to write your answer. Yes?
If it was 2, 3, 6, 7, 6, 8, 7.
Yeah, good. If that would have been like a 6 or something, then you'd have to say 2.4. Exactly. Yeah. Mm-hmm. Yeah.
Say it's 3, let's say it was 0.163.
Yeah.
Numbers, so then we need to have 3.
Well, if this would have came out to be 0.163, but if the 6 is the one where you have to stop at, there's only 2 sig figs here.
Because it's a bigger number.
Well, what I'm driving at is, if if you wanted to add a number there, I lost it. If you wanted to add a number there, it's kind of like where we were right here, right? Even though 5 is the, 6.5 is the answer, you don't do any rounding till the very end. So no matter what you get inside that parentheses, you keep all those digits. Just keep track of the number sig figs by underlining something. So this is a good example because this illustrates everything. Okay. Very good. So we're about out of time. Come by and I'll be glad to help you out with this. Give it a shot, and I'll be glad to. We can do some practice problems. Won't take very long at all, and